Hi everyone, this is Thiagarajan, retired Deputy Chief Engineer from Indian Railways. This video I would like to discuss something about the Hysteresis loop curve. The previous videos I have told about the principles of a long welded ride. There is LWR track and the perimeter locations where we can lay the LWR, and also the maintenance activities, how they have to be carried out. Okay, what are the precautions we are supposed to carry out. Keep it in mind. Okay. So also I have roughly told about the IRSE loop curve in the previous video. So this video I will say in detail about the IRSE loop curve. What is the loop curve and in what way it is helping us. Okay. So whatever you are seeing in the screen, it is a IRSE loop curve. It is a graphical representation of the expansion contraction of the LWR. Okay. And also just I want to recollect, repeat things, whatever we have seen in the first video about the principle. You see, when there is a temperature variation, there will be expansion contraction in the breathing inlet. Central portion will not undergo any expansion contraction, and there will be a setting of a force in the central portion. Okay. So there will be breathing only in the breath. There is the ends of the LWR. It's called a breathing length. Okay. For accommodating the expansion contractions, we are providing the switch expansion joints at the ends. So, and also as already discussed, the gaps, at the SEGs are to be inspected and checked periodically. Being it is an indicator, the gap will tell you that, about the performance of the LWR, whether the LWR is working properly or not. Okay. Other what we used to do, actually, we used to record the existing gaps. We will compare with the theoretical range of gaps prescribed. And for that we have seen various tables available. So many tables are there. Okay, and there we can find the range of gas for the different temperature and what should be for the various zones and various rail sections are available. Okay. So with that we will be able to check our LWR, confirm our LWR whether it is working properly or not. So how the theoretical range of gaps have been framed out on table. Okay. So that we are going to discuss now. That is all based on the IRSE loop curve only. Okay. And also further to explain, you see, actually this is our breathing length, both ends we have, and the expansion contraction will be only at the ends of only at the breathing length. You know pretty well the expansion or contraction is equal to the L alpha T. You know the principle, the scientific, the principle is there that the change in length equal to original length into alpha T. Okay, that all you have seen. But as far as in our scenario, our case, the expansion contraction only in the breathing length at the ends of the one end of the LWR, one end of the breathing length. So that is equal to actually LB alpha T divided by 2, because when a rod is free, it is free or completely uniformly fixed, there will be expansion contraction will be at the ends, and force, if it is a completely fixed, means there will be a force, full force will be there. The full force will be throughout the length, will be uniform. But in our case, you see here, the expansion will contract only on one end, and the other end there is no expansion contraction. That is completely stopped because of the building up of resistance. So here also you can see the force diagram is triangular. It is 0 at the one end and maximum at the other end, like that, and vice versa. Okay, where we have the maximum force, there delta L will be expansion contraction 0, and other end will be maximum. That is why, because of this, this one, and we will be able to conclude that our expansion contraction will be half of the L alpha T what we are having in a plane, in a plane rod. Okay. Considering this equation, that is delta L equal to LB alpha T divided by 2, substituting, already we know pretty well that breathing is equal to A alpha T divided by R. That means, our complete maximum force or due to temperature variations, there will be setting up a force in the central portion, that is equal to P, that P equal to A alpha T, A alpha T. For stopping the movement, the force is, the resistance is built up, because of the ballast resistance, which offers, unit ballast resistance is offering, and at one point completely the moment is restricted. There where we have the maximum force. At the same time, the moment is completely restricted. So that thereby, we'll be able to, get the length of breathing length equal to force divided by R. Force divided by whatever force, okay, divided by R for this one. How much for resistance is required for stopping the movement. So using the relation, finally, we got the A alpha, the P by R, A alpha divided by R. So substituting this one in place of LB, we get the A alpha T squared whole square divided by 2R. So this is the formula. As far as the breathing is concerned, the expansion contraction equal to A alpha T whole square divided by 2R. R is the ballast resistance. This is very, very important formula. And another formula also is there. The delta L equal to A alpha T whole square divided by 2 into double the ballast resistance. Okay. So this is all the main two equations available, two formulas are available. Based on this only, we are arriving at the movement, the expansion contraction with various temperature, and finally we are plotting the curve. We used to say it is this loop curve. Okay. So let's go to the next slide. We will discuss further what is this loop curve, why we have the two equations. This equation you pretty well, you are clear, because already we know delta L equal to L alpha divided by 2, and substitute is very condition. But why we are again modifying the formula like this, A alpha T whole square divided by 2 to double the resistance we are going, we'll see in the next slide. Okay. So actually the I'll just put some lines. You can just understand first, then we'll go to the explanation. The hysteresis loop is due to the behavior of the longitudinal ballast resistance, actually, because you see, whenever there is an expansion, and there is an expansion, there is an offering of resistance is there. The ballast offer resistance and controlling the moment and stopping at one point. Okay, that you understood. Actually, when we are installing the rail with the sleepers fastening down at a TD temperature, okay, then when let us assume that temperature is increasing trend, the temperature is increasing, what will happen? The rail is the breathing length, breathing length portion. The rail is trying to expand. At the same time, the ballast will offer some resistance. Normally, already, we studied that ballast is equal to R. Okay, R. That is unit ballast resistance we have seen. Okay, some kg per meter per rail or kg per centimeter per rail, it is there. But after increasing for some, temperature, some degree, then when it falls down, what will happen? The resistance will be double actually. The mobilization of resistance will be double. It will not be equal to R, it will be double. And because of the doubled resistance, there will be lagging. For example, when 10 degree temperature increase is there and further 10 mm expansion will be there, but 10 degree fall is there and 10 degree contraction will not take place, only 5 degree contraction will be there. 5 mm contraction will be there, because that's called lagging. So that is called hysteresis. Normally, the meaning of hysteresis is lagging. Okay, that's why, and whatever based on the the formula, we are calculating some extension, contraction and plotting it, and used to the curve is hysteresis loop curve. Okay, so all based on the ballast resistance. Okay, that's what it means. And just you can go through and understand, and finally we will discuss. The ballast resistance first increases linearly as sleeper displacement, then goes into the plastic zone and finally assumes a constant value R. If at the stage the temperature reverses, then the value of the longitudinal ballast resistance drops to 0 and then becomes minus R. This shows that at the time of reversal of temperature, the ballast resistance per place is 2R. This is something what it says. Okay. Then we'll see the next slide. So further to explain, you see, this is our rail and sleepers are firmly fixed. Normally we are fastening down the temperature, decreasing temperature, and whenever there is an expansion, there will be offering of opposite. There will be offering of resistance will be there. That will be equal to R. Okay, that will be equal to R. And as I told you, when the temperature increasing from a TD we are fixing, and assuming that the temperature is in increasing trend, and temperature is increasing, there will be expansion. At the time, the amount of resistance offered by is equal to R. But after some degree increase of temperature, it falls down, and when it falls down, this resistance will be double the resistance. Okay, double the resistance, because you see, when the sleeper, when the ballast offers some resistance, there is a fluctuation in the sleeper and under the packing, and goes to the offers the resistance R, and expansion takes place, and immediately there is a reversal takes place, temperature decrease takes place. When it is coming back, it cannot immediately will not become R. The whatever resistance, it has to come to 0, or to come to 0. Then one more resistance is required, for counteracting the movement. So there will be mobilization of double the ballast resistance. So only in the case of insulation to the increasing or insulation to the decreasing. So we used to have the resistance that equal to the magnitude of the resistance equal to R, and subsequent movement, subsequent reversal, again increasing, decreasing and all, our mobilization of ballast is equal to 2R. So that is why, and already we have told the second equation, the first one have been modified with the second one, and instead of R, and we are substituting 2R, that we are substituting the double the resistance. Okay, so using that only, and we are plotting the Hysteresis curve. Okay, as already told, there will be lagging, and because of that, there will be the whatever amount of the expansion takes place or contraction takes place for some degree will not be equal to the same amount, will not be equal when it falls down. Okay, it will be half of that only. So that is why there is a lagging. That's why we used to say the naming as hysteresis, because meaning of the hysteresis is lacking. Okay. So again, this offer, the subsequently all this one, this way, that way, this way, that way, it is 2R only. Okay, 2R only. So here actually this is at TD temperature, it is at rest 0. Then when there is extreme to expansion or contraction, there will be offering of resistance, it goes to R. And again reversal takes place, temperature reversal takes place. In that case, it has to come back to 0, then further resistance takes place. Okay, so there will be mobilization of 2R, that means double the resistance is taking place. That is why, and with this phenomena only, this principle only, we are calculating the expansion contraction and plotting the map, that's called Hysteresis loop curve. Okay. Okay, this I will say to see. Let us assume actually this picture shows we are installing the rail with the sleeper fastening down at a TD. Now the temperature increases. That means increases. Then we have the formula delta L equal to AE alpha T whole square divided by 2R. So that means from TD, when temperature increases to T maximum, That is the formula, because only first initial expansion or contraction after the insulation. So when it goes to the, let us assume it is going to this side, like maximum side. So the amount of R will be R only. Okay, magnitude of the R only. Then after reaching the maximum, reversal takes place. Temperature falls down. When it falls down, as I told so there will be mobilization of double the resistance. That is why. So this curve, the curve. This curve, because as far as our formula is concerned in square. That's why it is not non-linear equation. It will not be straight line. It will be curve only. At the same time, the amount of after reaching an expansion, after reaching the maximum expansion, because of the temperature falling, there will be contraction. The contraction will be half of that only, because of the double the mobilization of ballast. The contraction will be half of that only. So with using that relation, and every degree, every 5 degree or 10 degree, and we are plotting, and we are coming back to D, and again now temperature after coming to T minimum, then increases and gradually increases steadily and going to T maximum and completing the cycle. So this will be is called a hysteresis loop curve. It is only the assumption, because it is only the assumption that temperature TD after insulation, and gradually it will go to T maximum, then falling gradually steadily, and T minimum, then again steadily increasing and to T maximum. But in a actual scenario, it will not be like this. Okay, not big, because what will happen? See, when there is temperature increase, there will be falling down again, like that. So subsequently again after increase, then again falling, then increase. So like that, subsequently here is going up, then again falling down, then again falling, then increase, then falling, like that. So many loops, if you take in a day, there are day and night will be there, the temperature fluctuation will be there, increase, decrease, and if you are doing that, plotting and working out the expansion, contraction, and plotting the curve, and there will be so many loops like that. Okay, many loops will be there. Like that, the annual, this loop is being drawn. If we are drawing it, there will be plenty of loops, lines will be there. Okay, so this will be there. So after enclosing, covering everything, the full enclosing the entire loop will be the major loop. That will give you the fair expansion, contraction, how much will be there, and where various degree of temperature. Okay, so this covering that. Suppose for example, for particular this is your temperature. This is your y-axis, this is x-axis. Y-axis normally upside expansion, downside contraction. Like that, the x-axis right hand side rise, okay, temperature increase, and left hand side temperature fall, that is minus. So here plus, this is minus. Suppose some TD minus 10 degrees centigrade, TD minus 20 degrees, if you want to, this will be your range. This will be the amount of expansion, how much, and amount of contraction, how much. So using this one only, we are calculating the, finally, tabling the gaps, the range of gaps, because this is only not a gap, this is only the expansion, contraction for the particular temperature, how much variation, how much expansion, how much contraction can happen at a particular temperature. So as I already know, pretty well, we are providing initial gap of 40 mm initial gap, and with reference to reference line, we are having one side 20 mm we are having. So 20 mm initial gap at the time of TD temperature, and from there, if there is an expansion, suppose let us assume here upside is here some 5 mm, downside 10 mm contraction. So upside 5 mm expansion, what will happen? Expansion, once Rayleigh's expansion, SCJ, expansion is there, tangential side expansion is there, the gap will be reduced. That means 20 minus 5, 15 will be there, gap. Like that, when the contraction, how much? 10 mm contraction is there for this, for the particular temperature. That means once the contraction, there will be more gap will be there. So 20 plus 10, that means 30. That means 15 to 30 mm gap. That is the range. So this is what it says. So from that we are able to compute, for each and every degree temperature, with reference to TD, how much gap should be there, and based on that we can compute and we can table them. Okay, this is something about it. So, and instead of doing that roughly, and we are doing this one, plotting this curve, and we are there are two methods are there, and we can check even each method there are two situations will be there. If that is the case, we want to draw axis loop curve, we can draw four such loops, the major loop, 4 loops we can make. After plotting, overlapping one by one, plotting all 4 loops, we can find the maximum, how much maximum expansion, how much maximum contraction will be there. We can fix, and from there we can compute the gaps, theoretical gaps. Okay. The first method is temperature rise from T to T maximum, fall from T maximum to T minimum, again rise to T maximum from T minimum. That means what? This is the first case. That means after installation of rail at a TD, temperature increase from TD to T maximum, then falls down to T minimum, then increases to T maximum, completing the cycle. Okay, this is one method. Okay, use the relations and formula, 2 formulas. I mean this for this line we are using the first formula, and subsequent all these things dropping down and increasing to T maximum, we are using the second formula. This is movement in initial direction, this one, and subsequent to all movements, we are using the second formula. That means place of R we are putting double the resistance, that is movement in reverse and subsequent directions. Okay, this and another method. Okay, in this method temperature fall from TD to T minimum, rise from T minimum to T maximum, and then fall from T max to T minimum. That means from T here TD temperature installation we do, and after that there is we are assumption these are all assumption only, but actual scenario will not happen because every day there will be fluctuation, but we are assuming from TD to temperature steadily decreases to T minimum, then increases to T maximum, then again decreases to the gradual steadily T minimum, and complete cycle. If that is the case, okay, for this line for this one initial, for this one from TD to T minimum we are using the first equation, and subsequent one we are using the second equation. Okay, so based on that, for your understanding purpose, I have made an example for zone 2 and 60 gauge rail. For zone 2 we have 60 gauge rail section. Okay, and with this I want to work out the gaps available for gaps, how much gaps will be for various rail temperatures, and I want to plot it, and we are plotting it how our system will look like, and how from that how we are picking up our maximum expansion or contraction of the particular temperature, how we are computing the range of gaps for the different temperatures. Okay, and we can just compare with the table given. So this is for zone 2 and 60 gauge rail. So already delta L alpha T, already we have studied delta is breath length equal to L alpha T, and breath length is equal to A alpha T divided by R, and substitute we have the equation of delta equal to A alpha T square divided by 2R. This is only first equation. This is first equation. And for all the thing we require, we want a cross section area. Already we know we take 60 gauge rail section. For that 76.86 square centimeter is the cross section area of the rail. Young's model is pretty well for the rail still 2.11 into 10 to the power 6 kg per centimeter square. And alpha is the coefficient of linear expansion, that is alpha equal to 1.15 to 10 to the power -5 per degree centigrade. And temperature variation, I am keeping acidity as a variable because we will be able to work it out for various variation, for 10 degree variation or 5 degree variation, 1 degree variation, we can find out. That is why I am keeping it acidity. Then ballast resistance R, we have taken 112.98 kg per centimeter per in terms of centimeter I am taking it. Because normally I used to say 1000 kg per meter per rail or 1200 kg per rail. Okay, but because I want to substitute here in terms of in centimeter per rail. That is why it is 12.9 kg per centimeter per rail. That is based on the table. No, they have considered only 12.98 for this 60 kg rail. That is why I am taking as it is the same basins I am considering here. Okay. Then expansion contraction initial. Okay, initial I am telling you initial. This is actually this I am working on for the second method. That means from T to T minimum, then goes to T maximum, and finally coming back to T minimum. Okay. So here from T to T minimum first initial we are using only straight formula same the basic formula AE alpha T squared divided by 2R. Okay, that we are using. And second one modified formula. That means instead of R we are putting double the resistance, because subsequent expansion contraction will take place with and with the double the resistance only. Okay, so substituting the everything we are getting here actually everything in centimeter, and to get a value in mm I am multiplying by 10 now here. Suppose here for expansion for this case 0.00829 into 1 t square in terms of t. For 1 means 1 square means 0.0089 into 1. For 2 square means 2 square, 2 into 2, 4 plus 0.003 mm. So in terms of t I am keeping as variable. This is the equation. This is the basic formula. And subsequently the modified formula giving the double the resistance, it will be divided by 2 actually. Okay, this is 0.00415 into t squared by a. T squared mm. This is 2 value we got. With that we will be able to work it out for the variation of different variation of temperature, how much the expansion contraction. Okay, as I already told you, this is for the second method. Second method means from D to T minimum, then T maximum, then coming to T minimum. Okay, so here also I am two situations. One situation as far as zone 2 is concerned, what is the range of this temperature? Tm to Tm plus 5. Okay, Tm. Sometime we can do Tm, and sometime maximum of Tm plus 5 also. In diameter also we can do. But we are saying extreme this thing I am just taking. Okay. If you do our TD at Tm, what will be the this one? Okay, expansion. Okay. If you are doing the Tm, both sides 30 degree variation will be there. Lower side and upper side. Because now when you do TD at Tm, and it variation how much, it will go up to 30 degree down, and again it will rise, goes to TD and maximum 60, then again coming down to 60 like that. So both sides 30 will be there. So that is why TD actually 0 movement will be there, and TD minus 10 I am using the first formula, basic formula 0.00829 into 10 squared T squared minus 1, and TD minus 20 T in place of 20 20 squared 30 squared. So this will be your movement because of the temperature decrease, because TD to T minimum there is a minus means contraction, minus 1, minus 3, minus 7. After reaching the T minimum the reversal takes place. Reversal means temperature increase takes place. So T minus 30 to T minus 20, that means 10 degree increase is there. And in that case, because the reversal we are using the modified formula, that is 0.00415 into 10 squared. Okay, 10 squared. This will be your now expansion. Okay, after contraction is the end. After that, now because of increase there will be some expansion. So expansion now, once expansion there will be resultant movement. That means already minus 7 mm was there, and minus 7 mm. Actually, contraction we are considering minus sign, and expansion we are putting plus sign. So minus 7 here plus 0.00415 into 10 squared plus minus 7 equal to this one, or minus 7 plus this one will be equal to minus 1, because of the variation is very negligible. That's why it is as it is coming live. Subsequently 20 degree variation, 20 squared. So minus 7 plus this one minus this, like that 30 squared minus 7 plus this one. Okay, Then it goes to now after TD, again subsequently all because of increase only. It increase going up to 60 degrees centigrade because from T min to T30 and it goes back to T maximum 60. So 60 degree variation. So here you see minus 7 and that means maybe the 14 here. 14 minus 7, 7 we got here. Okay. So here and all maybe something 6 or 6 is 8 minus 7 is minus 1 like that. So we have come up to now TD plus 30, that is maximum. We have come to maximum, T maximum will come and this will be your the resultant moment plus 7 is there. And after that temperature falls down from T maximum to T minimum will go. So 10 degree decrease from TD plus 30 to TD plus 20. 10 degree decrease is there because 10 degree decrease here plus 7, this is minus 1. So plus 7 minus this one will be equal. So because the minimum there is the same value we got 7. Here again 20 degree variation is there. When TD plus 30 to 20, then 20 degree variation. So 20 degree variation plus 7 minus 0.041 20 squared equal to plus 6. So like that we are calculating for each and every 10 degree variation goes up to T minimum and finally we got minus 7. Okay, this is so for each and every temperature I am taking only a 10 degree variation. I am taking T minus 20. This is a expansion or contraction minus 1, 20 minus 3, minus 30 minus 3, minus 20 minus 7, minus 10 minus 6, and TD it is minus 4, and plus 10 it is minus 1, and plus 23 mm, and plus 37 mm, plus 27 mm, plus 10 6 mm, TD 4 mm, and minus 10 1 mm, and minus 23 mm, and finally minus 30 it is 7 mm. This is your expansion contraction. Plus represents expansion, minus represents contraction. Like that, another situation when we are doing this thing at Tm plus 5 degrees centigrade, and how much will be the expansion contraction. Similar way we are doing it here. After TD 0, TD minus 10, here also TD to T minimum is just falling. First, this is only first basic formula. First formula we are using it. This portion is like a modified formula, double the resistance. This one may only one single resistance. And with that we are calculating it is minus 1, minus 3, minus 1, minus 10. And after reaching the T minimum minus 35, here minus 35 because we are doing the TD equal to Tm plus 5 degrees centigrade. So upper side, lower side, we are first going from TD to T minimum. That means this side is 35, upper side 25. Okay. So that is why we are going up to TD minus 35. Okay, 35. This will be the value. Then after that, after reaching T minimum, minus 10, and now temperature increases there. 5 degree increases there here. T minus 5 degree increases there because TD minus 30 here. So 5 degree whatever expansion is there, plus this is plus. So minus this one plus this one will be minus because of minimum. It's same thing we got. So like that here minus 10 this value plus 1 number difference is there, that is why minus 9. Like that from T minimum temperature increase 30 20 10 TD plus 10 20 and finally it goes to T maximum of TD plus 25 degrees centigrade, and for that we got a 5 mm. Okay, the resultant here 5 mm expansion is there now. 5 mm expansion is there. The 5 mm keeping here 5 mm, keeping here 5 mm. Further now decrease, temperature decreases from TD plus 25 to TD plus 20 and 10 TD minus 10 minus 20 minus 30 minus fall is there. So after 5, so again we are working out here 0.45 plus 5 minus of this one will give them minus plus 5, and this one plus 5 minus of this one gives 4. Like the region every 10 degree variation temperature we are finding out, we go up to TD minus 35 and finally here minus 10 will be there for TD minus 35. So this last one column gives you the for various temperature how much contraction expansion. Okay, as I told you, minus represents contraction, plus represents expansion. Okay, two situations. Similarly, we can do for the other method also. That means temperature from TD to T maximum, then falls to T minimum, then again goes back above T max. That also we can find. So like that, if we do for two methods and two situations, each methods two situations, there will be four loops we can draw. So if you are drawing it, we will be able to get the maximum how much expansion of the particular temperature takes place and contraction how much you can find out. Okay, we will see how it is plotted. So I just manually plotted this one. Actually, it is not clearly color is not visible. The first TM means when we are doing the recessing at TM, this will be the curve, and when we are doing the TM plus 5, the yellow green will be the curve. This will be the curve. Okay. After plotting it, we can just find out now. We are taking the considering the maximum one. Okay. This is only one method I have done. Like that, one more method also we can do. In that case, will be two more loops will be there. Okay. That I don't want to confuse you. That is only one method, and similarly we can do it. With that itself, we are able to get where the amount of value. Okay. Here you see, if you take this is TD plus 10. How much we are getting after plotting this one? This one is upper side. This also I had told you it is y-axis, upper expansion, down, contraction. This is x-axis, right plus value, and left minus temperature. Okay, this is temperature. Temperature. This is temperature. TD minus temperature. This is expansion contraction. This is temperature. It's missing. Okay. So for TD plus 10 degree centigrade, if you just from the graph, if you are able to read, you see 6 mm expansion, 6 mm maximum. Here also, here one curve, it is only somewhere it is 4 mm, but maximum, other loop it is coming 6 mm. Like that, here contraction how much? The one loop, red loop it is only 1 mm, but here green loop it is 2 mm. So I am taking the maximum one. So maximum expansion is 6 mm and maximum contraction is 2 mm. Okay, TD plus 10 expansion. Like that, if you take TD minus 10, the maximum expansion is 1 mm and the maximum contraction is 8 mm. Okay. So this is this one. So from there, how we are getting the resultant gap? 6 mm maximum gap, it is possible. In that case, when there is expansion, the gap will be reduced. So 20 mm initial gap, 40 mm initial gap, but with reference to one portion, the reference line, one side, our gap is 20 mm, the A gap is 20 mm. So 20 minus 6 gap, because expansion gap will reduced, 14 mm will be there. And contraction, if it is a maximum possibility, how much? 2 mm. That means gap will be more, that 20 plus 2, 22 mm. So range will be equal to how much? 14 mm to 22 mm as far as TD plus 10 degrees centigrade. Okay, and similarly for TD minus 10 degrees centigrade, this one here you see 20 minus 1 19 mm and 20 plus 8 28 mm. This will be the range. So we can simply compare with the table how much it is there, whether it is matching or not. We will check up. Okay, this we already told you. Okay, so coming to here TD plus 10 to 14 by 22. Okay. And so 14 22. Similarly, TD minus 19 plus 28. Here you see 19 to 28. This is the range actually. This is the range we are actually able to get plotting the IRSE loop curve. Okay. This is the way for various temperatures and various zones and rail sections that gaps have been calculated using the IRSE loop curve, and already that the detailed table of range of gaps have been framed out. Okay. I hope that you have understood something about it, and I have made only the two loops. Like the two more loops also we can make, and following the other method, another first method, temperature increase. This is only decreasing. The increase into T maximum and coming down and again go to the max. That also we can make it. Okay, this is something about it. It's called Hysteresis. This is because of the lagging. Okay, some effect is there. That is why that name of the curve used to say Hysteresis loop curve. Okay. Further, I want to say, as per the IRPWM, Indian Railway Permanent Manual, para 338 2B, actually the over the theoretical range of gaps what you have obtained, and the plus or minus 10 mm we can permit. Okay, plus or minus 10 mm over the theoretical range of gaps we can permit, because some allowance is given. There will be some mistake in fixing of a TD temperature, and as well as there will be some creep in the rail, and there will be loss of ballast resistance. Considering all those things, some 10 mm allowance is given, the above and below. So that is a plus or minus 10 mm over the theoretical range of gaps is permitted. When the existing gap falls within this range, it's okay. Okay. Otherwise, as already discussed, we have to go for the destressing of LWR. And also, the Annexure 3.9, they are given this is conventional sleepers, and Annexure 3/9B for wider base sleepers. So wider base sleepers, similar way we have to work it out, because the ballast will be differing, So based on that, again we have to work it out, and there are 4 situations, and we can plot the curves that will give you the idea of Faraday of the range of gaps. I mean, contraction and expansion, how much, and from there we can compute the range of gaps. Okay, as we have discussed earlier. This is something about your so this is loop curve, and how we got the theoretical gaps have been fixed. Okay, so with that we can conclude this video. Okay, thanks, and let's see in the next video. Okay.